Hello friends, in this video I'd like to solve the following problem from the Spanish Mathematical Olympiad, final round 1981, problem number 4. We wish to evaluate the following indefinite integral of cosecant of t minus 1 times cosecant of t minus 2 dt. And remember that cosecant, probably the least used trig function, is just the inverse of sine. So cosecant of alpha is 1 over sine of alpha. This problem, though it looks innocent, turns out to be pretty hard, in my opinion, and tedious. My hints for this problem, first of all, use the fact that 2 times sine of alpha sine of beta equals cosine of alpha minus beta minus cosine of alpha plus beta, and many other trig identities you shall see. Second, our integral can be solved, simplified, using universal trigonometric substitution. Then it might be helpful to remember that the following is true, that integral of 1 over x squared minus a squared equals 1 over 2a natural log of the absolute value of x minus a over x plus a. And then the final hint, try to simplify your answer as much as possible, because the simpler the answer is, the easier it is to verify by taking derivative. So give this problem a try and see you in a moment. Okay, so I hope that you managed to solve this integral. My try is as follows. So we take our integral, and I will write it as sine t minus 1 sine t minus 2. And from the first trig identity, which I hinted, it's the same as the integral of 1/2 cosine of 1 minus cosine of 2t minus 3 dt. Okay, so we can put 2 in the numerator, and we have 2 dt in the numerator, cosine of 1 minus cosine of 2t minus 3. Okay, now let's make our first substitution. So let's introduce a new variable. So let u be equal to 2t minus 3. 2t minus 3. Then du becomes 2 dt. And our integral takes form of the integral of du cosine of 1 minus cosine of u. Okay, it's a bit simpler now. The next step, because we have a rational function of cosine of u, the following so-called universal substitution will work. So now we will substitute the following. u, or v equals tangent of u over 2. Why? Because it's a well-known fact. I don't want to prove it now, but then it so happens to be that du becomes 2 dv over 1 plus v squared, and also cosine of u becomes 1 minus v squared over 1 plus v squared. It's a well-known fact. You can check it on the internet that it is the case, or you can, from this formula, you can derive the following two as well. Okay, so our integral now becomes, instead of du, we have 2 dv1 plus v squared, cosine of 1 minus, instead of cosine of u, we have 1 minus v squared, 1 plus v squared. Okay, so let's simplify it a little bit. So we have 2 dv, and after a bit of simplification, we will get the following in the denominator: 1 plus cosine of 1 v squared minus 1 minus cosine of 1. Okay, perfect. And now let's stop for a while before continuing, and let's write these numbers in different form. Namely, I will use make use of the fact that cosine of 1 is 2 times cosine squared of 1/2 minus 1, which means that 2 times cosine squared of 1/2 is 1 plus cosine of 1, and also cosine of 1 is 1 minus 2 times sine squared of 1/2, which implies that 2 times sine squared of 1/2 is 1 minus cosine of 1. Okay. And now our integral becomes 2 dv. Instead of 1 plus cosine of 1, we can write 2 times cosine squared of 1/2 times v squared minus 2 times sine squared of 1/2. Perfect. And now we can write our integral in the following form. First of all, we can put cosine squared of 1/2 before our integral. And now we get dv v squared minus, and now sine squared over cosine squared is tangent squared of 1/2. Okay, very well. And now using another hint which I gave in the beginning, now I will make use of the fact that the integral of dx of x squared minus a squared is the same as 1 over 2 times a natural log of x minus a x plus a. Okay, and now we can write cosine squared of 1/2, and our integral, because we have a variable squared minus some constant, it's 1 over 2 times tangent of 1/2 times the natural log of the absolute value of v minus tangent of 1/2 v plus tangent of 1/2, plus some constant, but we will deal with any constants at the end of the video. And now let's simplify it further, because here we have 1 over cosine squared of 1/2, and tangent is sine over cosine. So we have cosine of 1/2, 2 times sine of 1/2. And now, instead of v, let's go back. V was tangent of u over 2. So we have tangent of u over 2 minus tangent of 1/2, tangent of u over 2 plus tangent of 1/2. Amazing. So somehow. And now we can simplify it further. So we have 2 times cosine of 1/2 sine of 1/2. And now let's take our argument of natural logarithm and let's multiply both the numerator and the denominator by cosine of u over 2 and by cosine of 1/2. And after a bit of simplification, we will get sine of u over 2 cosine of 1/2 minus cosine of u over 2 sine of 1/2, and very similar will be the denominator, but we'll have a plus. Very well. And now here we have a formula, the formula for sine of double angle. So we have 1 over sine of 1. And here using another trick identity, in the numerator we have sine of u minus 1 over 2. And in the denominator we have sine of u plus 1 over 2. Okay, 1 over sine of 1 is cosecant of 1. And here, let's go back with our substitution, because remember that u was 2t minus 3. 2t minus 3, so let's put it. Absolute value of sine 2t minus 3 minus 1 over 2. Sine of 2t minus 3 plus 1 over 2. And here, after simplification, we have sine of t minus 2, t minus 1. And that is our answer, namely integral of cosecant of t minus 1 times cosecant of t minus 2 dt. It's cosecant of 1 times the natural log of sine of t minus 2 sine of t minus 1. And very important, many people get it wrong, plus some function c of t. It's not exactly constant. Why? Because if you think about it, this function, its domain is not an interval. Its domain is sum of intervals. So because domain of our integral is not connected, this part need not be constant entirely, but this part, c of t, is a constant function on each interval which is in the domain. So c of t is constant on every connected part of the domain of this function. And that closes our problem. So we have, with a bit of pain, we have established that our integral equals this quantity, and we have noticed that this last part, this function is not constant, but it needs only to be constant on every connected part of the domain of this function. And that's it. So thank you for watching. I hope that you learned something new. Hope that you managed to follow my reasoning, all that substitutions and so on. And yeah, I wish you a nice day and see you next time. Bye.